Hello, everyone. Welcome to March 31st edition of Math 371. Quick reminder, your online homework is due on Friday. So today we're going to take a look at section 4.5. I have a new stylus, so hopefully my handwriting's a bit better today. So today we're going to talk about dimension. It's a concept you know well from maybe physics, but we're going to define it in terms of our language of linear algebra. So we're going to have a theorem, and then we're going to sort of show you why it's true. So if a vector space V has a basis curly B, which has these n vectors, then any set in V with more than n vectors is automatically linearly dependent. So for example, in the vector space R3, real numbers with their vectors with 3 entries are real numbers, any set of 4 vectors must be linearly dependent. So we're not going to prove this exactly, but we're going to show why it's true. So let's look at the case of n equals 2. Let's look at the case where n equals 2. Okay. What that's telling us is that our basis, B, has only 2 vectors, B1 and B2. So let's look at this set of vectors. U1, U2, and U3. These are 3 vectors, and we want to ask, are they linearly dependent? Well, we don't really know much about these vectors, but we do know that we can write them in terms of basis B. We can write them in terms of basis B. So each of these are vectors in R2 actually. These are vectors in R2. So I'm going to describe it a little bit more as we get familiar with this notation. But let's look at an example here. We know that U1 can be written as some combination of B1 and B2. We know this is true because the vector space V is equal to the span of B1 and B2 because those 2 vectors are a basis. Well, what this would tell us then is that this vector is the vector CD. So we see that this vector has 2 entries. It's an element in the real numbers squared. So let's take these vectors, and what do we always do? We want to put them in a matrix and row reduce. So we look at the matrix A, where we have these 3 column vectors. This is a 2 by 3 matrix. It has 2 rows, and has 3 columns because there's 3 vectors. If I row reduce it, what do I notice? Row reduce A. what happens? So think about it for a second. If I row reduce it, I know I must have at least one free variable. So at least one free variable tells us that there is a non-trivial solution to this equation. And that in turn tells us that x times u1 plus y times u2 plus z times u3 is actually the zero vector, which implies that this set is linearly dependent. All right, so we did all that work and we see that what's happening is I have more columns than rows, so I must have a free variable, therefore it must be linearly dependent. So you can see why this is true, that if I have more vectors than elements in the basis, if I write out a matrix like this, it must have a free variable, and therefore they could not be linearly independent. So the immediate consequence of that is the following theorem. If a vector space has a basis of n vectors, then every basis of V has n vectors. All right. The proof's pretty easy. Let's say I have two bases. And let's say the number of vectors in B2 is greater than the number of vectors in B1. Well, by the above theorem, since B1 is a basis and B2 has more vectors than B1, B2 must be a linearly dependent set. But that's a contradiction. Because we said B2 is a basis, therefore it has to be linearly independent. So the only thing that we assumed that was wrong was that they had different numbers of vectors. So what this tells us is that every basis must have the same number of vectors, and we call that number of vectors the dimension. Okay, so the first thing we should say is that if I can span a vector space by a finite number of vectors, we call that vector space finite dimensional. And the dimension of V is the number of vectors in any basis. We say the dimension of the zero space, or sorry, the dimension of the zero vector space is defined to be 0. And if V is not spanned by a finite set, then we call V infinite dimensional. Okay, so we're not going to work a whole lot with infinite dimensional vector spaces because they're a lot worse. That's all I'll say about that for now. So I want you guys to work 2 examples. What is the dimension of Rn? And what is the dimension of P sub n, which is the collection of polynomials of degree n or less. All right, so pause the video and go ahead and see if you can figure out what these dimensions are. All right, for the first one, it's probably not a big surprise. The dimension's n. We've actually written down a basis before. It's the standard basis, where the basis elements are all zeros in the vector with a 1 in one of the entries. What about Pn? So Pn, let's look at P1 or P sub 1. So these are all polynomials of the form a plus bt, where a and b are real numbers. And if I look at P sub 2, that's all polynomials that look like this. What do I notice about the number of real numbers I need to define a polynomial in P sub 1? I need 2 real numbers. I need a and b. For P2, or P sub 2, I need 3. And so what we see here is actually the dimension is actually n plus 1, because the constant term adds a dimension. Okay, so I want you to do another example. Let's look at subspaces of R4. I want you to find the 0-dimensional subspaces, the 1-dimensional subspaces, the 2-dimensional, 3-dimensional, and the 4-dimensional. So go ahead and pause the video and think about what are the 0-dimensional subspaces, 1-dimensional subspaces, etc. All right, now that you've had a chance to do that, the first one's pretty easy. It's just the 0 vector. What about the next one? Well, it's the span of a single vector that's not 0. So what's the shape of it? Well, lines through the origin. So that's one way to think of one-dimensional subspaces of R4. What do you think two spaces are? Or what do you think the two-dimensional subspaces are? Well, these are planes through the origin. 3 are what we call three-dimensional planes, hyperplanes through the origin. What about four-dimensional subspaces? How many of those are there? There's only one, and that's all of R4. All right, so let's move on to subspaces of finite dimensional space. All right, so we're gonna have a theorem. It says the following. Let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded to a basis in H. H is finite dimensional. And the dimension of H is always less than or equal to the dimension of. So, although this statement seems obvious, it's important in math to make sure that even obvious statements are can be rationally justified. So that's part of the reason of being a math major is that even things that sound obvious are sometimes false, and so it's your job to be very particular to make sure that details check out. So in this case, we're going to check out one of the details, and we're going to prove that the dimension of H really is less than the dimension of V. So let's prove it. So suppose that we have a basis for H. These vectors are actually in V. And they're linearly independent. So what does that tell us? This tells us that n must be less than or equal to the dimension of V, because we already know, because if n were bigger than the dimension of V, this would tell us that our set was linearly dependent by the first theorem today. So therefore, we must have that the dimension of H is smaller than the dimension of B, or they could be equal. The other theorem just takes a lot of groundwork and is not that enlightening. So this all leads to another theorem called the basis theorem. So what this theorem tells us is, let V be a p-dimensional vector space and P is going to be at least 1. any linearly independent set of exactly p elements in V is a basis for V. Also, any set of exactly p elements or vectors that span V is automatically a basis. Okay, so this involves understanding what the basis is and how that's going to interact with the span and the basis. Okay, so let's work it out, and you're going to see how you can rely on previous theorems to figure this out. So for the first part, we know, so let's prove the first part. We know that every basis for V contains exactly p vectors, because we know that the dimension of V is p. So let's look at the first part. Let's say that we have a set C and it has p vectors. And we want to know, does the span of C equal V? Well, let's say it doesn't. If not, there is a vector, we'll call it Cp plus 1 in V, so that this equation here is inconsistent. So what that tells us is that the set, if I include this new vector in it, is a linearly independent set. But this is actually a contradiction. Since the dimension of V is P, we know that in a set with more than P vectors is linearly dependent. Hence, we can conclude that the span of this set C was equal to V, and C is a basis. All right. So that was what we proved here, was the first statement that said that any set of P linearly independent vectors in a p-dimensional vector space must be a basis. So now let's prove the other statement that if I have p vectors that span it, it must be a basis. So suppose that I have the set D and the span of D equals V. Is D linearly independent? Well, if not, then you can remove vectors from D and preserve the span. So let's do that until D is a linearly independent set. So let's just get rid of some vectors. And let's say we reduce it down to, call it M vectors, where M is less than P. And now this set is linearly independent. And what this tells us then is that D is a basis for V with M vectors and M is less than P. But this is a contradiction. We know that every basis for V has exactly P vectors. Therefore, it must have been the case that D was linearly independent and D was a basis to begin with. All right, so that was a lot of theory, and now we're going to do some examples. So I want you to determine the dimensions of the null space of A and the column space of A for this matrix. All right, so pause the video and calculate what's the dimension of the null space and what's the dimension of the column space, just for some practice. All right, now you've had a chance to do that. Let's circle the pivots. We see there are 3 pivots. So this must tell us, and we have 2 free variables. So this tells us that the dimension of the null space of A must be 2, and the dimension of the column space of A must be 3. So the number of pivots gives us the dimension of the column space, and the number of free variables gives us the dimension of the null space. All right, that's a little practice that we'll be seeing more of soon. And I want you guys to also show that these vectors form a basis for P4, sorry, P3, piece of 3. We know this is 4-dimensional. So what that means is you have one of 2 options. You can either show that these 4 vectors up here, either show that they are linearly independent, or show that their span is all a piece of 3. All right. So make sure you do that in your notes. Moving on to 4.6, we're going to revisit some theorems with the column space and the null space. that we saw before. And we're going to introduce another concept. So if A is an m by n matrix, each row of A has n entries. And can be identified with a vector in Rn, because you have n real numbers. So the set of all linear combinations of the rows of A is called the row space of A, and is denoted by this notation right here. We call it row of A. So observe, row of A is the same as the column space of A transpose. All right. So this is a similar concept to ones that we've encountered before, but it's a little bit different, and our row operations will be a little bit different as well, how we interpret them. So here's a theorem that you're going to find useful. If two matrices, A and B, are row equivalent, that means you can get to one from the other using elementary row operations, then they're row spaces. Then the row space of A is equal to the row space of B. Furthermore, if B is an echelon form, the non-zero rows of B form a basis for row B, which is equal to row A. Okay, so let's prove this. So we need to show that the basic row operations do not change the span. So we need to show that elementary row operations do not change the row space. Okay. So let's look at, and let's kind of talk about why this is true. Observe that the rows of B are combinations of the rows of A. So what this should tell us is that the row space of B is smaller than or equal to the row space of A. Makes sense. I can produce all of the rows of I can produce all the rows of B from the rows of A. However, elementary row operations are all reversible. which tells us that we can obtain the rows of A using combinations of the rows of B. And that tells us that the row space of A is smaller than or equal to the row space of B, and therefore we conclude that they're actually equal. All right, so now we know that their row spaces are the same. And when it's in echelon form, it's pretty clear that those are linearly independent vectors that span it. So what I'm going to have you guys do is do some examples where you compute row A, row B, and all those fun things. So, example, I want you to find a basis for the column space of A, the row space of A, and the null space of A. So A is going to equal this matrix. And if I row reduce it, I get the following. So go ahead and work in your notes and identify a basis for the column space, the row space, and the null space. All right. Now you've had a chance to do that, let's work out what we can. So the column space of A is the span. Well, let's see. Here are the pivots. So the pivots are right here. So we take the columns in A, where the pivots are, and the span of those will equal the column space. All right, so those two vectors form a basis for the column space of A. What about the row space of A? Well, we have the pivots in rows 1 and 2. So we take the rows from the B matrix on the right as our basis elements. Last but not least, we need to find the null space of A. That's the same as the null space of B. So we know that x1 is going to equal x3 minus 5 x4. And let's see, if I do a little algebra, x2 should equal 5 halves x3 minus 3x4. Okay, so if I have my vector of solutions, it should look something like this. Okay, so if I do a little work there, this should tell me that the null space of A should be the span of 1, 5 halves, 1, 0, and -5, -3, 0, 1. All right, so that should be the span of the null space. So I'm going to give you another example to work in your notes. Again, to find bases of the column space of A, the row space of A, and the null space of A, where A is this relatively large matrix. That row reduces to B. All right, so go ahead and work that out in your notes. And we'll move on to one last theorem. And this is a theorem that you've seen before, but we need to define two things before we go. The rank of A is dimension of the column space of A, and the dimension of the null space of A is sometimes called the nullity of A. So this gives us what's called the rank theorem. Which tells us the following. If A is m by n matrix, then the dimension of the row space of A is the same as the dimension of the column space of A. They're not the same, but their dimensions are the same. And this is equal to the number of pivot positions in A. And the rank of A plus the dimension of the null space of A is always equal to n. So last but not least, I'll give you a couple examples to work at home. If A is a 6 by 8 matrix, what is the smallest possible value for the dimension of the null space? If A is a 4 by 3 matrix, what is the largest possible dimension of the row space? What if A is a 3 by 4 matrix instead? So work these problems out, put them in your notes, and I will see you all soon. Let me know if you have any questions.